Today's lesson is a hodgepodge of review items, but I actually want to start with something I don't think we've actually gone over, at least up till now, which is the difference between inertial mass and gravitational mass. And this is what's provided by the AP. The gravitational mass of an object determines the amount of force exerted on the object by a gravitational field. So if you're using mg to figure out the gravitational force, then that is gravitational mass. Or if you're using the mg m over r squared, that would also be gravitational mass. If, however, you are just using F net equals ma, and you're just trying to prove that applying a force will cause a mass to accelerate in the same direction, then you are using this as inertial mass, which is basically a take on Newton's first law, which states that an object at rest tends to stay at rest until acted on by an outside force. And the more mass something has, the more inertia it has, the more resistance it has. So that if you have, just say an 8 Newton force acting on a 2 kilogram mass, it's going to accelerate it much more easily than if it was, say, an 8 kilogram mass, because the 8 kilogram would have more inertia and more resistance to being accelerated. So all this means is that you need to understand that objects and systems have properties of inertial mass and gravitational mass that are experimentally verified to be the same and that satisfy conservation principles. And you might need to, on the AP, design a plan for collecting data to measure gravitational mass. So, that could just be literally using a scale. And then inertia mass. And so for the inertia mass, you would have to come up with some sort of F net equals ma experiment where you would know the force and you would measure the acceleration and then determine the mass that way. Now I'd like to talk about some things that will be on the worksheet along with this lesson. If you have a mass that's just out in the vacuum of space, and let's say it has velocity, then it can have kinetic energy, which is 1/2 mv squared, but that's all it can have unless it's part of a system. Here it's part of a system because it's attached to a spring, so it can have, in addition to kinetic energy, it can have spring potential energy, which is 1/2 kx squared, k being the spring constant. And if it's part of a pendulum, then it's also part of a system because Earth is part of that system. And then you could have potential energy, gravitational potential energy, which is mgh. A quick reminder about springs. If you have a mass and it's attached to the end of the spring, and you just pull on the mass with an applied force, the spring force pulling back is equal to negative kx. Negative just because it's pulling one way in the opposite direction of the applied force, which our frame would say is positive. So k is the spring constant, and x is simply how far you're pulling the spring from its equilibrium position. So in this case, we have an applied force that has stretched the spring, and let's say the applied force is 4 newtons, and we'll say it's pulled the spring 0.5 meters. So we could use that to find k. So if the applied force is negative of the spring force, then it follows that the applied force will just simply be k times x. So k in this case is the applied force over x, which would be 4 newtons over 0.5 meters, or 8 newtons per meter. If we take the same spring and look at it as a vertical spring and we pull it down, well, we could just use the weight of the mass to pull it down. And the weight of the mass, if it was 0.4 kilograms, would just be 4 newtons. And if we had the same spring with the same spring constant, and we're pulling with the same applied force, we would expect to have the same distance pulled from the equilibrium, or 0.5 meters. Let's do a quick review of a spring's energy. We know that work is force times displacement and that they have to be in the same direction. Well, in this case, they are. So we could say that work is kx times x. That would almost be true, except remember, when you pull on a spring, it's the average force that is doing the work. And the average force is the final force, the force when the spring is all the way out, minus the initial force divided by 2. But the initial force is 0. Hence, work is just kx over 2 times x, or 1/2 kx squared, the potential energy of a spring. We haven't talked much about spring oscillations, but if we have a spring on a table and the spring has been pulled from its equilibrium position by, say, a maximum distance of x, we also can call that the maximum amplitude of the spring. Because of the wave-like feature of the spring, which will oscillate on either side of the equilibrium position. Eventually, friction makes it stop. The spring goes fastest while it was going through the equilibrium position. That's where it has the most kinetic energy, or 1/2 mv squared. And at that point, it's exactly equal to the potential energy it had at the start. Similar to how a pendulum, which is working against gravity, the pendulum also will just go back and forth until it eventually stops in a wave-like oscillating pattern. And it has potential gravitational energy, which is mgh, and that will supply all the energy for the maximum kinetic energy, again, 1/2 mv squared, and once again, that occurs at the equilibrium point. Finally, we'll talk a little bit about power today. We've talked about power before. We said it's the rate of doing work over time or expending energy over time. We may have talked a little bit about the fact, however, that power can also be looked at as force times velocity if the force and the velocity are in the same direction. Here's just a quick example of that, and this will appear on your worksheet. Let's say someone's dragging a large box across the floor, and they're pulling it with an applied force. And let's say they pull that box a total displacement of 4 meters, and let's say the force is 100 newtons. So we could figure out the work pretty easily. The work, even if there's some friction, the friction just keeps it from accelerating. And let's say in this case we are pulling it at a constant velocity of 2 meters per second. Well, the power would be work over time, so the work would just be 100 newtons times 4 meters, which would be 400 joules of work. And we need to know the time. So let's just say that the time here was 10 seconds, something like that. So we'd have 400 joules over 10 seconds, or 40 watts of power. If we had just looked at that from a force times velocity situation, we could have said the force was 100 newtons and the velocity would be just the change in displacement over time, or 4 meters over 10 seconds. So 0.4 meters per second times 100 would be 40 watts, same thing.